Today's my lecture topic is regenerators. Heavy duty regenerators are designed for applications in large gas turbines in the 1 to 50 megawatt range. The use of regenerators in conjunction with industrial gas turbines substantially increases cycle efficiency and provides an impetus to energy management by reducing fuel consumption up to 30%. The term regenerative heat exchanger is used for the system in which the heat transfer between two streams is affected by the exposure of a third medium alternately to the two flows. The heat flows successively into and out of the third medium, which undergoes the cyclic temperature. In a recuperative heat exchanger, each element of head transferring surface has a constant temperature, and by arranging the gas paths in central flow, the temperature distribution in the matrix in the direction of flow is that given optimum performance for the given heat transfer conditions. This optimum temperature distribution can be achieved ideally in a counterflow regenerator and approached very closely in a cross-flow regenerator. In the regenerator, the most present-day regenerative gas turbines, ambient air enters the inlet filter and is compressed to about 100 psi, that is 6.8 bar, and a temperature of 500 degree Fahrenheit, that is 260 degrees centigrade. The air is then piped to the regenerator, which heats the air to about 900 degree Fahrenheit. The heated air is then enters the combustor, which is further heated before entering the turbine. After the gas has undergone expansion in the turbine, it is about 1000 degree Fahrenheit and essentially at ambient pressure. The gas is ducted through the regenerator, where the waste heat is transferred to the incoming air. The gas is then discharged into the ambient air through the exhaust stack. In effect, the heat that would otherwise be lost is transferred to the air, decreasing the amount of fuel that must be consumed to operate the turbine. For a 25 megawatt turbine, the regenerator heats 10 million pounds of air per day. The combustors, all gas turbine combustors, perform the PEMS function. They increase the temperature of the high pressure gas. The gas turbine combustor uses very little of its air, that is 10% of the combustion process. The rest of the air is used for cooling and mixing. New combustors are also circulating steam for cooling purpose. Air from the compressor must be diffused from it enters the combustor. The velocity of the air leaving the compressor is about 400 to 600 feet per second, that is 120 to 183 meter per second, and the velocity in the combustor must be maintained below 15.2 meter per second. Even at these low velocities, care must be taken to avoid the flame to be carried on downstream. The combustor is a direct fired air heater in which fuel is burned almost automatically with one-third or less of the combustor discharge. Combustion products are then mixed with the remaining air to arrive at a suitable turbine inlet temperature. Despite the many design differences in combustor, all gas turbine combustion chambers have three features. One is recirculation zone, another one is burning zone, third one is dilution zone. These three zones are very important.